So what happens is that the measure branches, as you would say in Everettian terminology, into two instances, one of which sees a 0, and the other of which sees a 1. Becoming entangled is really easy. I mean, it happens all the time. The thing that's difficult is to make it happen in a controlled way so that you can also undo it again. So usually, the fact that things are entangled is kind of hidden from view. Because if you're residing here, the system doesn't seem entangled to you at all. Like, it seems like the system is just in the state 1. It's not an entangled state anymore. You can make the environment more complex by saying that there's also an environment prime and environment prime. And they're also interacting with the system. And the more that they interact, the harder and harder it will become to re-interfere the states of the qubit and the measuring instrument. This branch will henceforth evolve roughly independently from this one. It will give us a preferred basis in which to analyze the system. Even if you're, for example, in a quantum computer and you're performing, some CNOT gates or some measurements gates are being applied within the quantum computer, there's still a history there that prefers one basis over another basis.
Hello, welcome back to the Quantum Foundations podcast. I'm Marie Villaris. I'm just finishing a PhD at the University of Oxford in Quantum Foundations. Today I'm joined by Sam Kuypers, who is a postdoc at the University of Montreal and previously did his PhD at Oxford in the same group as me, supervised by Vladimir Medrel. So this podcast has two parts. One part is aimed to be more accessible for an audience who has an interest in the topic, and another part which is aimed at people with some background in quantum mechanics that have taken an introductory course in quantum mechanics and explains things in mathematical detail. So the previous episode of the podcast was the accessible version, and this is the mathematical version. And the topic for this podcast with Sam is the many worlds theory of quantum mechanics. So today we're going to dive into the many worlds theory on a mathematical level and try and understand how to solve some of the problems in the theory mathematically. So thanks for joining, Sam.
Thanks for having me. It's fun.
Great. And let's start discussing many worlds.
Yeah.
So for viewers that may not have watched the other episode and kind of familiar with quantum mechanics, but maybe haven't thought so much about interpretations of quantum mechanics, could you give a little summary of what the many worlds theory is and a bit of context on the role of interpretations of quantum mechanics?
Yes, so the many worlds interpretation is a solution to the measurement problem. The idea being that there's generally, as we said in the other podcast, there's two types of evolution. One of them is unitary. The other one is something that happens during measurement, which seems to be reversal. It's called collapse. And collapse is problematic for all kinds of reasons. And the solution that Everett offered is to just have everything be unitary and then explain the appearance of collapse that seems to happen during measurement in a way that is also unitary. So it's explaining more with less in a nutshell. That's the plan. And the role of interpretation means science is, I forget if you mentioned this in the other podcast, but I think science is about explaining the world. Mm-hmm. And when we talk about interpretations of quantum mechanics, I think it's almost a little bit misleading because it's very hard to distinguish the mathematical formalism from the explanatory content of the theory. So there's all kinds of explanations in quantum theory. Some of them are rival explanations, like there's collapse and then there's many worlds, for example, that we just mentioned. And the question for me is really which one is the better explanation, which one allows us to explain more, which one is more universal, which one is better tested, things like that. Sometimes testability comes into it, sometimes it doesn't. But the goal is always to explain. So I think this is a quote by David Wallace, where it's either Wallace or Deutsch. he said that, if you look at fossils, I think it's Deutsch, in fact, if you look at fossils, then our explanation of why fossils are there is that there were once dinosaurs, things like dinosaurs, which we then see in fossil records.
Mm-hmm.
And to say that that is an interpretation of the fossil record is a little bit perverse. And it's, the theory is that we're really dinosaurs. They roamed the earth and then they died and then went extinct. And that's why we see the fossil record as it is now. And quantum theory is much the same. It's a little bit perverse in the dinosaur case to say, well, that's just our interpretation of fossils. Our interpretations there. There are these things in theory that we call dinosaurs. It's much more parsimonious and I think also honest to say, no, they were just dinosaurs. That's why we see them in fossil record. It's nothing to do with a specific interpretation or anything like that. That's just the explanation of fossils. And in the same way, although there's not necessarily consensus, I would still defend Everett as being the same kind of explanation. That we have an explanation of the world in terms of quantum mechanics, and we should care about it because we care about explanations, even if it's wrong. It might, even for people who would disagree that many will necessarily think we should care about scientific theories in this way, just because that's science is about explaining the world. And that's what Everett attempts to do.
Cool. Great. So I'm convinced that we should care about interpretations now.
Cool.
So now that we all care, if not, it's probably not the video for you.
You're still welcome.
You're still welcome.
You're still welcome. We'll still try to persuade you.
Yeah. Still see some nice maths and neat, satisfying things. Okay. So what is the many worlds theory and how does it solve the measurement problem?
Yeah, maybe we should start with what is collapse, because that's the main it's the thing it's opposing, so to speak. So just to make sure. Yeah. Yeah, everything is going as planned. So I always like to do stuff in terms of qubits because we both have a quantum information background. I guess people that watch videos might also have that interest. So qubits are nice.
Yeah.
The thing about qubits is that they have a bunch of observables and then states. The states are simplest, so let's write them down. For example, they have the states 0 and 1. So these are a set of states of the qubit.
Mm-hmm.
And they correspond to an observable. So if we measure the observable that we call z prime z, then by measuring it, we see either a 0 or a 1, one of these eigenstates. Now, in general, the state of the system can be written in terms of these two components. So we have a qubit, and it can be written as some kind of superposition of 0 and 1, right? And the thing that happens during measurement is that because we observe only one of these two states during a measurement, so we measure the observable sigma z, which gives us one of these two outcomes. And that means that when the system is in superposition, it will probabilistically collapse into one of these two states. So we perform a measurement. So perform a measurement on this system, and then say we end up in a state 0. So after the measurement, the state is 0.
Mm-hmm.
So that's a kind of dynamics. As I said, it's probabilistic. We don't know which outcome we're going to observe. All we know is that we're measuring a certain observable, and therefore we're going to see one of its eigenstates. In this case, I picked out one of them. It's happened to be 0, but we can't know that beforehand.
Mm-hmm.
And this is not how systems evolve generally. Generally, they evolve unitarily, which means that they evolve deterministically, reversibly. So this, as you can see, is already not reversible because with some probability we pick up one of these states, but we can't tell beforehand which state that would be. First, we have to update the state. We can't you can't reverse this process. It's so those are the two types of evolution that we have. Is a unitary is good to discuss as well. Do you want to know what the unitary evolution is? Maybe it's
I think it's good to discuss.
Yeah.
So, what is unitary evolution?
So unitary evolution, I think, the most important parts about it are that it is reversible. The reversible dynamics that the system undergoes when it's not being measured. So what we just discussed is this is what the system does when it's being measured. It probabilistically collapses into one of these two states, hence the name collapse. And the unitary dynamics are reversible, and they're the thing that happens in a more general case. So whenever your system is not being observed, it evolves unitarily. Unitary evolution, let's see, what's a good example in the case of a qubit? For example, we might have the unitary which performs the NOT gate. If our initial state here were to undergo a NOT gate, then that is the same as the unitary acting on each of these components. Which is something we've defined above. And then we have a little dynamics of the qubit undergoing the NOT gate, which is clearly reversible because you can just apply the NOT gate twice, and then you're back at the original state. The thing that defines unitary evolution in general is that the unitary, so for example, NOT gate, has a Hermitian conjugate such that if you multiply it with itself is the unit. So that's the definition of a unitary in general. So this is kind of the way systems evolve. Generally, there's unitary evolution, and then this is collapse.
Yeah. So the key message with unitary evolution is that whatever you do to your qubit or your system as a whole, there's always this valid other thing you can do which will undo it. So you can always, anything you can do, you can undo. So it's intrinsically reversible. Whereas in the collapse case, it's non-unitary because you could see that because it's irreversible. Because if you'd gone from this superposition of 0 and 1 to picking up 0, then there's no operation you can apply that will uniquely take your 0 back to this superposition and your 1 back to that superposition.
Yes, because these coefficients, so these are the complex value coefficients, can be inconsistent different values, and it will still be the same dynamic. So if you want to do this, as you said, in general, so in a specific case, it might be that you can have an operation which sends you from 0 to that superposition. But the weird thing is that these coefficients can be different, and then you have to send the state back to a different superposition. So you can't, in general, get to the reverse operation, even though in specific instances you might. The general case does not work. Those are the two different kinds of evolution. And it's very strange that there are these two types of evolution, because the unitary type explains so much of what we see. So unitary quantum theory is the quantum theory that we invoke when we are trying to actually explain how a system works. Like if you're doing quantum field theory, if you're doing condensed matter theory, then quantum computation, the kind of the meat of the explanation is in the unitary part of the theory. And then in a kind of ad hoc way, we have to also allude to the collapse model, because we actually want to make predictions. We want to be able to say, okay, well, so if we then observe the system, what are we likely to see? Because again, collapse doesn't allow for specific predictions. Generally, it allows for probabilistic ones. So that's a weird mix of things. It's two different kinds of dynamics. One of them seems to be quite fundamental. It's invoked in kind of the general case. There are cases where things don't seem to evolve unitarily, but that's usually because they're a subsystem of a larger system. So that you can always view the larger system as being the one that looks unitarily, and then the subsystems appear not to. And so that really allows us quite a lot of systems, a lot of different explanations in physics rely on the unitary part, and then the ad hoc part is needed, but is also very ad hoc. So, for example, one question you might have is, when did you perform a measurement? Like we allude to that as being a thing that we know about. But that's not really a theory that we say, well, we know what we're doing in the lab when we perform a measurement. So we know when collapse happens roughly. But in theory, the theory I've just provided doesn't really specify what I meant with a measurement. So that's one question that you might have at this point. Like, what is a measurement? What is a measuring system? Is it that there is perhaps a cutoff between where quantum theory is valid and where classical physics works? So that, very large systems like the tables and stuff that we see around us, and the chairs and maybe, ourselves and other objects, that these systems seem to be they seem to be classical in the sense that the table has a definite position, has a definite mass, and all those things. And perhaps it is that these systems can perform measurements on the quantum systems. So that's what involves that's what produces the collapse. There's large systems that behave roughly classically, and that they allow us to peer into the quantum world for us to perform measurements on them. And then one question you have is, well, tables are just large systems consisting of many atoms. Atoms are quantum systems. How many atoms do you need for something to be a classical system in this setting? And I think whichever trajectory you go down, because there's many of these types of questions you can have about measurements, you always find some problem that doesn't quite work. You always have to, in some way, limit the applicability of quantum physics. Because, for example, in this case, you're trying to limit it by saying, well, it doesn't apply to very large systems. Well, our theories in quantum matter physics don't really allow for that, for example. So, for example, the fact that this table is robust is something that is explained by quantum theory. Classical physics does not allow it to explain the formation of atoms and things like that. And in fact, things like the rigidity of objects like tables is explained by quantum matter theory in a completely quantum way. So again, trying to limit the explanatory power of quantum theory seems problematic. And it's the thing that you would generally have to do. So it's the thing that people attempt whenever they want to explain measurement. And the route that Everett took is to say, well, let's not try to limit the explanatory power of quantum theory in that way. Let's just say that it applies to everything, including, for example, the measuring instruments, which are made of atoms, and which are described by quantum theory, therefore, and see what we can get. See if we can get something which perhaps doesn't start with collapse, so it assumes only the unitary part of the theory, and which then produces the collapse, the appearance of collapse as a conclusion of that. So that's what we can do now.
So when we apply, Everett's innovation was to say, let's solve this problem of having the unitary evolution that we use to make sense of understanding things, and this non-unitary evolution that we need to explain how we've retrieved an outcome. Let's reconcile that by just taking this unitary evolution to be universal, to apply to everything, and then see if an explanation for us retrieving method outcomes comes out.
Yes. Yeah. So it's, as I said at the start, we want to explain more with less. We want to kind of say, well, this thing, the collapse part, let's not assume it. Let's scrap it for the moment. Let's see if we can do without it.
Yeah.
And then explain, as a conclusion of unitary quantum theory, why collapse appears to happen during measurements. And also let's try to find what a measurement actually is. Let's give it a better explanation of what that could be. Because again, we haven't really specified it. We've just said, oh, well, such a thing. And I've alluded to common sense, but it's not in the theory itself.
Yeah. Please show us what.
Cool. Will do.
How can we solve these problems? What really is a measurement?
Okay, so let's see. I will erase this part for the.
Does it scroll?
I can make a new layer.
Yeah,
that's it. Yeah. So, so the first thing we want to do is say that we have a measuring instrument that has some state M0, which is the ready state. So that's a measuring instrument which hasn't yet done anything. We've prepared it in such a way that it can perform a measurement, meaning that it can interact with, for example, qubit, which will again be the system that we're interested in.
Mm-hmm.
And when it measures a qubit, it should end up in a state that reflects what it's seen. So, for example, we can specify that if the measuring instrument sees a 0, meaning that it interacts with. In fact, let's do away with the not. It's just n. So this is the ready state of the measuring instrument. We say it interacts. So there's a measurement interaction. And in this case, what will happen is that it will go to state M0, which may or may not be different from the initial state, meaning I saw a 0.
Mm-hmm.
And likewise, if the qubit is in state 1, then the measurer should end up in a state M1, which means I have seen a 1, or it was a 1.
Mm-hmm.
And so that's kind of a simple model at the moment, that we have something, we have a measuring instrument, it's a quantum system, so that's an assumption.
Mm-hmm.
And it has at least 2 orthogonal states. So we want to make sure that we can distinguish these two. So M0 and M1 should be orthogonal.
Mm-hmm.
So that the outcomes are distinguishable from one another. And such that the labels mean these specific things. So M0 means it was a 0, and M1 means it was a 1.
Mm-hmm.
And it is a good measure if it ends up in those states after interacting with 0 and 1 in this way.
Mm-hmm.
So, for example, a bad measurement would be one which, this is not what we'll consider, but just for illustrative purposes.
Mm-hmm.
If it says it was a 1, but it actually saw, it was a 0, but it actually saw a 1, then that would be a bad measuring instrument.
It's like a measurement with an error.
Yeah.
It's told you the wrong thing.
Exactly. Yeah. So we want to avoid that. So we are assuming our measuring instrument is a good one.
Yeah.
So that doesn't happen.
And do you have an example to think about of if I'm imagining if I measure a device out my qubit, I guess I could just imagine whatever it is that tells me 0 or 1 is this quantum system.
Yes. So real measuring instruments are quite complicated, and we're kind of simplifying it down to it has to have at least 2 states, might have more. But there has to be at least 2 distinguishable states which say it was a 1, it was a 0. So it could be that you have a little screen that says it was a 1, it was a 0. But the actual measuring instrument can be quite complex. So it can be much more sophisticated than what we're displaying, because we've abstracted away all the inner workings.
Mm-hmm.
But the important thing about how it works is that it can do this exact thing. So if it can do this, at least, then it's a measure. It can also do other things besides that. And it can have internal structure, which is much more rich than what we're considering here. But that doesn't matter so long as it does this. And that's kind of our useful abstraction.
Uh-huh.
So this seems to work quite well in cases where, for example, the qubit really is in state 0 or 1.
Mm-hmm.
In which case, I would say unambiguously see that some kind of measurement has been performed. But now, of course, the real question is what happens if the system is in superposition? Because that seems much less straightforward. Like, what would it see if I try to perform the following operation in a setting where, the system is in superposition.
Mhm.
And also, I should maybe say that this can be implemented with a unitary transformation. So, perhaps even before you do that, it's nice to give an even more concrete model. So this is kind of the general procedure.
Mhm.
And now we're going to simplify it down even further by saying, well, the measuring instrument might be another qubit. So that's a very, very simple measuring instrument
Mhm.
in some way. So we can say that the state that we talked about before, these states, we're now going to implement it with a qubit using a CNOT, so that we have discussed both the kind of the more general framework for it, but also the specific instance of it makes clear that the system really is unitary. And it makes it maybe a little bit more concrete because we know about things like CNOT gates, and we know we have like a set of measures, but we can make it another qubit. So, for example, it could be that we have
So now we're in a special case of saying, here's an example with qubits of a measure.
Yes. Yeah, exactly. So we're going to assume in this simple case, the measure is a qubit.
Mhm.
And then its ready state might be 0. So the ready state of the qubit which acts as the measure might be 0, and the qubit that is being measured is also in 0, the state 0, in which case the CNOT makes it go to 0, 0. And if the measuring instrument is in state, the ready state 0, and then the qubit is a 1, then the CNOT makes it go to 1, 1.
Mhm.
So here we see that we have exactly what we required above. For example, 0 and 1 are indeed orthogonal. And it's just the same dynamics that we wrote down above. And as I said before, this ready state of the measure doesn't necessarily have to be different from the state it ends up in, which you can see here. So if the qubit is in state 0, then nothing will happen to the measure. And then we know that after the measurement has taken place, it being in state 0 means the qubit was also in state 0.
Mhm.
So, and maybe also for clarity, there's things that happen when the measure is in state 1, which we want to know about, not so much for our case, but more because the CNOT is defined in all of them. And we want to make sure that it's unitary. So you can see again that if the qubit being measured is 1, then a NOT gate is applied to the measuring instrument. So in this case, it was a NOT. And here again, if the qubit being measured is a 1, then a NOT gate is applied to the measuring instrument. So it goes from 1 to 0.
Mm-hmm.
And we're only interested in these ones.
Yeah.
But for anyone who's interested, you can work out that this is unitary from these specifications,
Mm-hmm.
Which you could not work out if we hadn't provided you with what it does in these other states. So this is a full set of basis states. Everything else that happens can be written as a superposition of these guys. So people can't see what I'm pointing at. So these guys are the full basis of states.
Yeah.
And we've told you what happens to each of the basis states. And you can see that it's reversible.
Mm-hmm.
In fact, applying it twice is exactly the thing which reverses the dynamics. And so now we've shown this is a unitary theory. And we've shown what happens within this unitary theory if you happen to be in an eigenstate of the sigma z observable. So if you happen to be in eigenstate 1 or 0, it's very clear what happens. But now the question everyone has is what happens if it's in a superposition? So
Mm-hmm.
we have these rules now. I hope people can read my handwriting.
Superposition.
Yes.
Yeah.
We've said it, so you can decipher it using live steps. So again, we're working with the qubit. The qubit might initially be in state 0. So that's the measuring qubit is in state 0. That's its ready state. then there's some kind of superposition of the qubit that's to be measured, which is in either state, well, it's in state 1 and 0 at the same time. And now, because we specified what happens to each of these states, you can also see what happens to the more general case of the superposition, which is that you will end up in this state. So what happens is that the measurer branches, as you would say in Everettian terminology, into two instances, one of which is the first one of which sees a 0, and the other of which sees a 1. So in the case of there being a superposition, the measurer in the unitary theory that we've invented, or that Everett invented, will observe both outcomes, but each instance of the measuring instrument will only have recorded 1. So if you look at the measuring instrument relative to the system being measured being 0, then the measurer will say it was a 0. And if you look at the system being measured, the qubit being measured, being in the state 1, then the measurer will say, well, it was a 1. But we, from our cold side point of view, can see, well, those two things exist at the same time in the superposition. So the measurer has both observed 0 and a 1 simultaneously, except they don't see that. They only see the one specific outcome, which is what explains the appearance of collapse. So the appearance of collapse happens because we observers and measuring instruments in general can only see specific outcomes, even though multiple happen at the same time. So that's where the idea of other universes comes from, because in the general case, these states will evolve from each other kind of independently, and yet they have these specific outcomes, and we know from theory that there must be other outcomes that have also been observed. So that is an intriguing conclusion, which we get from a completely unitary theory. So we assume unitarity, we can explain the appearance of collapse, and as a kind of unintended consequence, but not an unwelcome one, I think, it's unusual about it, is that there seem to be other branches. There seem to be other Everettian universes, as they're sometimes called. And they must exist at the same time as one another, so they all exist simultaneously. So yeah, that's the basic kind of overview of how the measurement happens and how we explain measuring in quantum theory.
Cool. And this measurement process is an entanglement. Entanglement created between the measurement device and the system.
Yes. Yeah, so that's a good point that we should stress that initially the system and the measuring instrument were not entangled. And then due to the CNOT gates, they were entangled with one another, which explains both why each of them sees only one outcome. So they're entangled with one another. So when the qubit is in state 0, the measure is in state 0, and when the qubit being measured is in state 1, the measuring instrument is in state 1. Which, that is a feature of that requires that they are entangled in this way. And entanglement is therefore the explanation of how measurements happen. You in the general case, you become entangled with whatever system you're measuring. And that's a lot of that is just the magic of the CNOT gate, which Deutsch once told me that he initially named the CNOT gate the measurement gate, which I thought was fun. It's an interesting little side note.
Yeah, it's a fun fact.
Yes.
Yeah. So I have a question relating to this, which might kind of lead on to the next topics, but it just came to mind that sometimes when I talk about explaining measurement via entanglement, people have this reaction of they'll go, but entanglement is like really delicate and difficult to maintain. And then you're saying that entanglement is happening all the time when this kind of easy way of when you make a measurement, you become entangled and everything becomes entangled. Do you have any comments on how to reconcile the idea of entanglement being difficult to create and maintain with entanglement happening all the time because it's the explanation for measurement and a lot of and interactions in general that are often entangling?
Yeah, well, it's becoming entangled is really easy. I mean, it happens all the time. The thing that's difficult is to make it happen in a controlled way so that you can also undo it again. So what people want to do during, for example, interference experiments is that you have something in a entangled state, and then you want to do an experiment on that system in such a way that you can see that it's in an entangled state. So usually the fact that things are entangled is kind of hidden from view, because if you're residing here, the system doesn't seem entangled to you at all. Like, it seems like the system is just in the state 1. It's not in a entangled state anymore. So if you're the measure, it's 0. It's a 0. So if you're the measurer, and you look at the qubit, you go, well, the qubit is just in state 0. But that's because the qubit is in state 0 relative to the measure being in that state 2. Just as the measure is in state 0 relative to the qubit being in state 0. And so the measure can see the other part of the superposition, which is the 1-1 state. So this part of the measure, I mean, so the instance of the measure that is a 0 can see the 1-1 state. So it looks as though from the branch as if the qubit is no longer in a superposition and as if the whole thing is no longer in an entangled state. So what you want to do is if you have some kind of experiment, you want to make the entanglement happen in a controlled way so that the whole time it looks like it is entangled, and you can perform a measurement on it that shows that. Whereas if you also become entangled with the thing you're trying to perform a measurement on, then it will seem as if it's no longer entangled. So it's the controllability of it. Like, things you really, really want to get entangled.
Yeah.
You want things to get entangled a little bit so that you can then undo it in a way that shows that it was. Whereas if it gets entangled too much, you can't do that anymore.
So the challenge to keeping nice, delicate entanglement is actually stopping yourself becoming entangled with it, because it really wants to get entangled with everything. And so, so the challenge of keeping the controlled entanglement is to stop the unwanted entanglement.
Yes.
Yeah.
Yeah. It really wants to get entangled, and it's not fragile in the way that it no longer is entangled. It's entangled too much.
Yeah.
And we want to stop it from being entangled too much so that we can perform the controlled experiments.
Yeah. So widespread entanglement is not delicate, but isolated entanglement is very delicate.
Yes, in general. Yeah. As Concepta was saying, there's other cases where sometimes you want the system to interact with other things, and that's hard.
Yeah.
So it's like, anyway, but that's maybe
there's always subtleties.
Yeah. And the subtleties. But then in general, that's true. Yeah.
Yeah. Cool. So when I look at this state and I see these two qubits into these two branches, it can then ask the question that I can kind of see, okay, this happened with these two qubits, but how can I explain how the whole world ends up in these branches and why I have this entire universe around me that feels classical?
Yes. Sorry. So, I mean, the appearance of classicality, what explains that? It's, so you don't see the superposition anymore. You see specific measurement outcomes. So you see the bits 0 and 1, which are here roughly. Like, those are classical things in a way. So first of all, I should say, when I can use the term classical from now on, like the Everettian quantum theory is universal in the sense that it doesn't really allow for such systems in general. I mean, there's the question of how does gravity work, and that's a problem. But in general, you now want to use quantum theory for everything. So there is only the appearance of classicality. And the bit is a thing which is kind of class. So the qubit can be in states 0 and 1. And whenever the qubit is in state 0 or 1, it's a little bit like it's a classical bit. And that's what we mean when we say, oh, that it appears classical from that point of view. It's just those cases in which it's not a superposition, which you have to think everything is kind of one of those uniquely or distinctly quantum aspects of the qubit. And what we see is if we try to measure the qubit, or if we measure the qubit, if we do in fact measure it, then we only see one of those two outcomes. So on each of the branches, so again, there's these two branches, and in each of them, you see only a 0 and a 1, and you don't see the superposition anymore. So that's part of the explanation of classicality, is that you see specific outcomes, and you generally don't interact so much with the other branch. Like in general, what will happen is that the 0-0 state and the 1-1 state will evolve basically completely independently of each other. So you can't really see that there's this other state, this 1-1 state, if you're the 0-0 state, because it's hidden from view. And it's like nature kind of hides it from view for us. And that's not clear from this yet, but because there doesn't really seem to be much of the system can do it. You kind of think that if this is quite a small system, so what will happen if the system's small as it is now is that it might re-interfere. These different branches might start affecting each other, just because if it's going to evolve, it only has a very small state space to explore, and it will explore the states in which it re-interferes as well. So generally what happens is that, of course, the measure and the qubits being measured are part of a much larger system, namely, so there is, let's see, how can we draw this? We have the qubit that's being measured, so we call that the qubit that's the system, and we have the qubit that does the measurement, and then there's also an environment that we'll call E. I don't really know why I drew that box. Maybe it's not necessary. So we have, in general, there's also an environment. And that's the thing that we haven't really incorporated yet, because if we have some system in the lab, say, well, the system in the lab is also interacting with lots of other quantum systems. If only because, for example, the air molecules are hitting the measuring instrument and are therefore kind of interacting with it. But in our previous example, so what we were considering here, well, you can't see the air molecules. There's nothing besides the measuring instrument and the qubit being measured. So it made sense to explore what happens in these more general cases where there is an environment which is doing something to the system being measured. And it is, maybe this is also a good point to mention the preferred basis problem. So we just explained the measurement procedure in which one qubit measures another qubit. And one thing that people also note at that point is, well, there's a kind of ambiguity in the measurement procedure. And what they do is they give us a specific state. So again, we have the measuring instrument, and then we have the qubit being measured, which in this case is an following state. Then we have the CNOTs, which is our measurement interaction. And then the state ends up in 0-0, 1-1. And the ambiguity was that if we define these states, these plus and minus states, and minus
Let's find. I think it's 0 minus 1.
Yeah, I
It's the
think
more,
so. Yeah.
more conventional. Yeah.
And now what we can do is we can say that the state 0, 0 plus 1, 1 is equal to, I was just mathematically writing it out, which will leave as an exercise to the viewer.
Homework.
Yeah, horrible. It's a bit too much to write out here. So either that or you have to trust some authority. But and we might be wrong. So that was the fun part, where I think that there's this plus sign here. I could be wrong, but I think there should be a plus sign. Perhaps there's a minus sign.
So you can check and let us know in the comments.
Yeah. So the problem is now that the plus and minus states were also orthogonal. And if we now reinterpret the state plus of the measuring instrument as being it was a plus, and the state minus of the measuring instrument as being it was a minus on the qubit being measured, then these look very similar. They look it's kind of uncanny how similar they are, because it now appears as if at the same time that this measurement was performed in the computational basis, there was another measurement that was performed in the plus-minus basis. And that is because of this ambiguity in which basis was being measured. This criticism is called, or this problem is called the preferred basis problem. Because in the real world, there is a definite measurement outcome. There's one of them happens, and for example, if you're in the lab, you measure which energy level an electron and an ion is, then you see one of those two outcomes. And there's no ambiguity about you having measured, for example, the energy level. Whereas this would suggest, well, you measured which of the two energy levels it was in, and it might be that you measured the energy levels, or you might have measured another state that the qubit was in, that the electron, the ion was in. And we can tell from theory which is which. So, yeah, that's something to be explained. It's not obvious why we should prefer one of these over the other. And the explanation I like, and which I think is kind of the accepted one among Everettians, is that although the state doesn't really give you any preferred basis in which the measurement took place, the dynamics does. So the dynamics of the system does give you a way of preferring one of these, so preferring either this one or this one over the other. And the reason for that is that if you perform a measurement in the lab, then usually the measuring instrument, because it is itself a quantum system, is interacting with some kind of environment. So the example I keep using is molecules of air are hitting the measuring instrument, photons are hitting it. There's lots of kind of going on that constitutes very subtle but important interactions between measuring instrument and other things that are in its environment. And those things are not included in the model so far. So what we want to do is we want to have a slightly more sophisticated model where we have both the qubits doing the measurement, so it's the qubit being measured, and it's QS. So we have QS, which is the qubit being measured, QM, which is the qubit performing the measurement, and then we have something we call E, which is the environment. And so that's going to model these other things like air, photons, debris or something, like slightly interacting with the measuring instrument. And what will happen is that, so we just had so we're going to write the same state again. So we have already performed the measurement with the qubit has. And then there is some state of the environment, call it E, which is a kind of, again, it's a ready state. The environment is in some arbitrary state such that it will interact with the measure and become, say, 0 So now we have a slightly more sophisticated model of measurement where we're not just modeling the qubit measuring another qubit, but we're modeling an environment that is interacting with our first qubit. So again, like with the measurement case, we are also assuming that these states of the environment are at least roughly zero, so they're orthogonal as well. And one thing that this will do is it will give us a preferred basis in which to analyze the system. And the reason for that is because the environment is interacting with the measurer in a specific basis. So there's a measurement interaction which is entangling the environment with the measurer in a way that is specific. There's a specific kind of interaction which is happening. So the dynamics can pick out which of these two states that we wrote before. So we have this other state, a plus plus state, and the environment can pick out, due to the interactions it enables with the system, which of those two is in fact the one that really happens.
So the way the environment interacts with the measurement device in the system is the thing which picks out a particular basis, and that's what dynamics are, as opposed to states, is the way it's interacted, or if we're representing it as a quantum circuit, the gates rather than the states. It's whatever is doing the evolving of the state.
Yes. Yeah. So it's the dynamics of the system will prefer certain states over other states, or certain bases over other bases. So the system has interacted with the environment, and it has interacted in a specific way, as I said. And one of the things that this will do is it will prevent interference between these branches from happening. So the reason is that if you want to re-interfere the states 0, 0, and 1, 1, you can now no longer just interfere those. You also have to perform an interference experiment that includes the environment.
Right.
So either you have to undo the entanglement of the environment, or you have to include the environment in the interference that happens.
Right. Yeah.
And that is a much harder task than just interfering 0, 0, or 0, 0, and 1, 1 of the qubit states. And what makes the problem worse is that you can in fact include more environment states. So you can make the environment more complex by saying, well, there's also an environment prime and environment prime. And they're also interacting with the system. And the more that they interact, the harder and harder it will become to re-interfere the state of the qubit and the measuring instrument. And that's roughly what happens in the real world, because of course, if molecule Ver hits the measuring instrument, and then the next molecule Ver hits it, and the next one hits it, that's the kind of like these additional environment states, and there's many of them. Afterwards, the environment ends up in these roughly orthogonal states, which makes interference harder and harder to happen. And it makes it harder and harder for that to happen in a specific basis. So these, or we call branches, this branch will henceforth evolve roughly independently from this one. So they don't really see each other anymore, because again, the interference between them is suppressed, and that's the only way in which they could see each other. They could see each other through interference, just being suppressed, and therefore you have these two branches in which the system will evolve forward in time. And you can also see from the density matrix of the system that there is this kind of preferred basis, because if we write the density matrix of the system, so the density matrix is we're going to call this whole thing is psi. And then the density matrix of the complete system is this state. So we call that rho. And if you want to have the density matrix of just Q and S, what we do is we trace out the environment, which gives us the classical mixture that looks as follows. Brackets. And now this mixture cannot be written in another basis. So there's a unique basis in which the system is diagonal. And it's these diagonal elements that will henceforth evolve independently of each other in the state that we saw here. So these diagonal elements don't really interfere. There's just kind of like a classical mixture of these two states. And it is due to the specific form of the interactions with the environment that there is such a unique way of decomposing the reduced density matrix of system QM and QS. So, that's where we get from the idea that in general, you can say there is some observable, say, called S, which commutes the interaction Hamiltonian, which is the thing that makes the interaction between the environment and the system happen. It commutes with that interaction Hamiltonian, and it's
So what is that symbol?
Oh, it's S. Yes.
Okay.
Yeah.
No, it does look like an S.
Yes. Okay. So it's just a random. I chose a random letter. Yeah. That we call S. There is a thing called S which commutes with the interaction Hamiltonian, and the reduced density matrix will be diagonal in terms of that, the eigensets of that observable. So you can see a connection here between this interaction Hamiltonian, which makes the interaction between the environment happen, and that picks out a specific state, a specific observable in which the density matrix, the reduced density matrix, is diagonal. So that's the logic of what I just described, where the dynamics tent picks out a specific observable, a specific basis that's being measured, because that's what this condition tells us, really. There is such a basis which is preferred over others by the dynamics, by the Hamiltonian, just because it commutes. So yeah, this is all known as decoherence. This is decoherence theory, and I think it's quite a nice solution because it's both a thing which makes the measurement much more realistic, and it is of general importance to lots of things. Like decoherence theory is not just important for the theory of measurement that I've described here, but it kind of explains lots of different things in quantum physics. Quantum physics often relies on the idea of decoherence. Like there is another spontaneous symmetry rating in quantum metal theory. It also relies on decoherence theory, and it has a nice reach. So it's not like we are inventing a little nice little niche theory just to explain away the preferred basis problem. It's really something that plays a big role in quantum physics, and it's also the explanation for why the preferred basis problem is not as problematic as we think it is. We can explain that quite readily.
Yeah, so this is just one of many applications of decoherence theory. It's like one consequence of it is it solves the preferred basis problem, but it's also a very powerful theory for lots of problems.
Yes. Yeah, so as I said, one of my favorite examples of it is in quantum meta theory, where large systems are very susceptible to decoherence, and then that plays a role in explaining magnetism and the rigidity of things like tables and crystals and stuff like that, which is quite neat. So yeah, Wallace has a paper on that, and it is so it's nicely unifying. We can use decoherence in other aspects of physics, and also we can use it here in Everett. And I think it makes the most sense in Everett because we decoherence is another thing which is a completely unitary process. So these interactions that we've written down are all unitary. In fact, the environment could be modeled as more qubits that are just enacting more and more NOT gates in a way that we can't control. And as I kind of saw here already, let me see, was it here? No, it must have been. Yeah, okay, so, yeah, it was on the slide here. So, what we've written here, where the environment becomes entangled with the qubit, that's basically exactly the measurement procedure that we wrote down earlier. The environment is in some initial ready state, then it performs, there's some interaction which we can't control, but which is the only difference between it and the measurement procedures we were discussing before. But,
Right, because they were in our control. This is one out of our control.
yes.
And the ones in our control we can manipulate to do strange things, whereas the ones out of our control, we can't, by definition.
Yeah. Yeah, so even the ones in, so there's a degree of control that we have over the measurement device. And then there's the degree of control that we have over the environment, which is much, much less. But in principle, the kind of thing that they're doing, so the measurement device and the environment, it's like they're kind of doing the same thing, because they interact in a certain way, then the environment records what outcome was observed according to the measuring instrument. And then there's another bit of the environment that observes what, or measures what the first bit of the environment observed, etc. So this whole chain of observations happening. And so that kind of functions in the same way. They're both, is the only difference, as we said, is that one of them is in our control, or more in our control, and one is completely out of our control. We can't control every error, every atom of error in the room that the measuring instrument is in. So that's where decoherence comes in.
So I have a question relating to this. So you have system, measurement device, environment. And we said we can, in this kind of simplified model, we can say measurement device and system, model the measurement by control NOT gate. And then we have environment and measurement device for environment and system, and we could model that by another control NOT gate. So why do I need to introduce the environment to solve the preferred basis problem? Why can't I just say that the dynamics of how the measurement device interacted with the system by the same logic? Can I not say that dynamics picks out a particular basis?
Yeah, I think you can. It's just, so the reason why this explanation is a little bit easier to understand is because first of all, there's the idea that you're not controlling the environment and it must be doing stuff as well. And there is a way in which the environment is interacting with the measuring instrument. And, but it is true that even if the system is in I just noticed this. It should be extra brackets here.
Yeah.
Anyway, so even if you're, for example, in a quantum computer and you're performing, some CNOT gates or some measurements gates are being applied within the quantum computer, I feel that there's still a history there that prefers one basis over another basis. So if you're computing some function in many, many different branches, but you're computing the function specifically in the computational basis, then your explanation of what the computer is doing is it is in a superposition of all these different functions being computed. And it's not doing another thing at the same time. Like in another basis, that would look like stuff is being scrambled.
Yeah.
So there, again, the dynamics of the system would pick out a specific basis for you. But at any point in time, you would have the preferred basis problem again. In the sense that if you don't have any history to it, if you just see the state as just in an instant, then the ambiguity arises again of which thing was measured and which thing wasn't. But in all cases, both in the coherent case, where it's just a quantum computer doing something without there being decoherence, and the case in which there is decoherence. It's only when you can see how the system is evolving in time that you can say that there's such a thing as a basis being preferred over another.
Yeah. So it's interesting about so having a preferred basis is it's a property of an evolving system, not of a static system. But yeah, it's a kind of interesting, maybe philosophical point, but yeah, that it's a property of the system as it's evolving, rather than something that you can define for a static one.
Yeah, it's weird that there is that distinction. I don't think we have. I'm not sure we have anything like that in classical physics, but well, in classical physics, maybe a thing which is similar is the role that the observables play. So if you look at, for example, position and momentum as abstract things, they're both vectors in a vector space, then it's not quite clear what their meaning is at any instant of time. But it's because of their role in the Hamiltonian and in the dynamics of the system that we say, well, this thing is momentum and this thing is position. And like if we were to relabel them and also relabel them in the Hamiltonian or something weird like that, then you couldn't see that. But it is the role that they play within the dynamics that makes you able to say, well, this thing is the velocity, this thing is the momentum of the system, this thing is the position of the system. So I guess that is kind of similar. If you abstract away the dynamics in classical physics, you have roughly similar problems, I would say.
Yeah. Oh, nice. Cool. So we have explained how measurement can be modeled in a fully unitary way, measurement device being quantum. It leads to emergent branches, which are the many worlds of Everettian quantum theory. And you've given an explanation for why these branches, why we only see single outcomes in these branches, definite single outcomes, and why we don't see these branches re-interfering with each other, because the entanglement kind of has spread all over to include this environment, which is then out of our control.
Yes.
And you've also explained how we get a unique basis picked out for these independent branches to kind of evolve along. And that's from the dynamics, which is how the system and measurement device and environment and everything are interacting. So the form of those interactions is picking out a unique basis.
Yes. Yeah, maybe we should have said as well that the observable in this case is exactly the Pauli Z that I was seen before. So it's the Pauli Z on, for example, a measuring instrument.
Yeah.
This is the system. It's the identity operator on the system that you can check. More homework. I'm generally against homework, but since we're near the end.
Fun activities.
Yeah. If you want to check yourself, it's fun. That the unitary of the CNOT gate commutes with the observable, the Z observable of the measuring instrument.
Yeah, that's a good point, because that is what shows us that the CNOT picks out Z. So it picks out computational basis as special.
Yes. I'll write this down on an extra page, and we can have it as an exercise. Because this is too much for the margin that I intended. But I can do that later.
Cool.
Yeah.
Yeah. So I think that was a very nice explanation of key aspects of the many worlds theory and Everettian quantum theory. So as we wrap up, do you have any final comments or words you'd like to tell our audience before we finish?
No, I hope that they liked it. And I was curious if people if people find it persuasive, if not, why not? Discussions are fun. So yeah, I will definitely check in the comment section of the video if anyone has anything to say that they'd like to share their criticisms, because of course criticisms are good.
Mhm.
And no, other than that, I mean, people can find me on Twitter if they want to discuss there as well.
Nice. We'll put a link to Sam's Twitter in the description.
It's cool. Yeah, other than that, thanks for having me. It's been really fun.
Great. Thanks for joining and giving such a nice explanation of things. And yeah, please do write in the comments any thoughts, criticisms, questions that you have. I'll be checking as well. And as I mentioned, we do have the other podcast, which was aimed to be more accessible. So you can listen to that as well, where we discuss various other topics as well, such as the probability issue and some other aspects about the many worlds theory. And please join next time for more quantum foundations discussions. Bye.
Bye-bye.
So today on News at Quantum, we have the many worlds theory.
Shocking.
There are claims that there are multiple universes from conspiracy theorists, physicists.
Insane people are claiming insane things. Hear about it here first.
Hello?
Hello.
Blah, 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 blah. Welcome to the podcast.
Yeah, that's really funny. We can see the orb
The orb.
here. Yeah.
The multiversal.
Yeah.
Yeah. After having solved the preferred basis problem, this is take 2. We're going to do some actual maths.
Some physics.
Real physics.
Actual physics. Oh, that's fake physics.